Oh, this is a quiet group. All right. You've got the next homework. That's not due until a week from Friday. So you have that, and you guys out there should also be able to have a copy of that homework. And I'll be grading the last homework tomorrow. Looking forward to that. And that'll be back to you on Friday. Okay. So what we're talking about here, we're talking about functions of two variables, and this section 14.2, we're talking about two concepts, whether they have a limit and whether they're continuous. And actually, the main concept here is going to be the limits. So 14.2, limits and what's called continuity. Now, I gave definitions of those last time. We'll be working with the limit definition today. As far as continuity is concerned, let me just say in very broad terms that a function is continuous if its graph, in this case, it's going to be a surface, has no holes in it. So a function of two variables is continuous if its surface graph has no holes in it. Or I guess we could also say sudden breaks. Okay. In other words, basically, if it just looks smooth, or if it's just kind of floating along in there. All right. Now, basically, we've been pretty much dealing with functions of one variable that are continuous, and so the things that we know are continuous are polynomials, certainly the trig functions, and the exponent function, log ln function. These basic type of functions that we've been working with are continuous. So in two variables, we're going to have basically the same thing. So let me put this down here. A function f(x,y) of two variables that we deal with will be continuous at the xy point a comma b for a specific x and y input value, as long as it has an actual value at a comma b. In other words, as long as a comma b is in its domain. All right. So as long as, for what we're going to be talking about, as long as a comma b is in its domain, the function is going to be continuous there. And some just very basic kind of examples as far as the polynomials are concerned. Now we have polynomials of two variables. So a polynomial of two variables. Something like f(x,y) equal, I don't know, x to the fourth plus 2x cubed y plus 3y squared, x squared plus 5y. Let's just say any combination of x and y, but it looks like a polynomial. It all has integer exponents. That's certainly a continuous function. Trig functions of two variables. certainly sine of x squared minus y squared, cosine of x plus y. Trig functions of two variables will be continuous. Exponent functions, we could have, say, e to the x squared plus 2y squared, something like that. That would be a continuous function of two variables. And then, of course, the ln function of two variables. Say, ln of x plus y. Oh, now that's tricky. And actually, let me put a star by that, because we'll have to look at that in just a second. In fact, for right now, let me just kind of cancel that out, because I'm going to talk about that in just a minute. But otherwise, these other functions, they don't really have restrictions on their domains, the ones that I put here, and so they're continuous throughout. Now, the problem here is what if we have functions of two variables that we have restrictions on their domains, okay? So what if we have fxy where there are restrictions on the domain? On the domain. In fact, since I just now talked about the ln function, let me do this one first. How about the ln of, let fxy equal the ln of, say, 4 minus x minus y. All right. Now, something that you saw on the exam was that where there was a question about the domain on the exam. We know that the natural log is not defined for 0 or for any negative value. So therefore, there's a restriction here. So therefore, what's in the parentheses here, 4 minus x minus y, has to be strictly greater than 0 for this to be defined. All right. So let's just do a little algebra here, adding x and y. Therefore, 4 has to be greater than x plus y, or in other words, put it the other way, x plus y has to be less than 4. So we can say here that this function fxy is continuous as long as x plus y is less than 4. So we could say it's continuous on the ordered pairs. Let me put bracket, x comma y, put that vertical line, that means such that, so x comma y such that x plus y is less than 4. And it's continuous for those values. Let's then look at another example. Let's look at fxy. This time, let's introduce a denominator, because that always causes problems because we can't divide by 0. So let's have x squared minus y squared divided by x squared plus y squared. All right. So this can't be 0. All right. So therefore, and when do we have a problem? We have a problem when both x equals 0 and y equals 0. That will give us the denominator equaling 0. All right. So basically, this function is continuous everywhere except at the origin of 0, 0. So we can say fxy is continuous except x continuous on the ordered pair x comma y such that x comma y does not equal 0 comma 0. All right, another way of putting it. So if you have homework questions that are asking you where is this function continuous, and you have limitations like a denominator or ln, then you want to exclude those places where we don't have the function defined for where it's continuous. One last example here where we have a radical. Let's have fxy equal the square root of x minus y. Okay, so we just want real values for our function, so therefore in this case we can't have less than 0 under that square root radical. Okay, now we can have 0. That's okay because it's not in the denominator. So therefore this function fxy is continuous as long as x minus y is greater than or equal to 0. Could be 0. And another way of putting that, if I add y to both sides, as long as x is strictly greater than or equal to y. All right? So we can say it's continuous on the set x comma y such that x is strictly bigger than or equal to y. Okay. All right. So that shouldn't be too big of a problem figuring out where our functions are continuous at. Now let's go back then to limits. And a lot of times finding a limit is really easy, because if the function is continuous at that point, then basically all we have to do is plug in those point values into our function and we've got our limit. So it's very simple. The difficulty can become if the function isn't continuous and we might still have a limit. Okay, so let's first of all just look at the easy case here. So back to limits. Okay. If we know fxy is continuous at a comma b, we just plug in a comma b for x comma y to get the limit. All right, so just a couple of examples of that. The limit as x comma y arrow approaches 1 comma 2 of, let's say, x squared y squared minus 3xy. Very simple. Just plug in 1 for x and 2 for y. So that's going to be 1 squared times 2 squared minus 3 times 1 times 2, which is 4 minus 6, which is negative 2. Very easy. Similarly, say if we have the limit as x comma y approaches, let's say, pi comma pi over 2. So we're approaching the ordered pair pi comma pi over 2, and our function is e to the x plus y times the sine of x minus y. All right. So we just fill in our values, pi for x, pi over 2 for y. So that's going to be e to the pi plus pi over 2 power times sine x minus y, pi minus pi over 2. Now this one can be simplified a little bit. This is going to be e, let's see, pi plus pi over 2 is 3 pi over 2. All right. And then what's the, and this is the sine, the sine of what, pi over 2. So what's the sine of pi over 2? Good, 1. So this is e to the 3 pi over 2 power. Okay. Just plug in the x and y. Okay. Now, so that's easy. Now what happens here though, the harder question is, how do we determine if we have a limit when the function isn't continuous? Okay, that's the more difficult thing. Because if it is continuous, we just plug in the values. How do we determine if a limit exists if fxy is not continuous at a comma b? All right. Now, in the text and for what we're going to, and for the homework and what we're going to look at, we're going to restrict our a comma b to 0 comma 0, to the origin. All right. So for our problem, we will restrict a comma b to just the origin at 0 comma 0. Okay. So we're going to be looking at functions. So we'll look at, yeah, this restriction. All right. So for what we're going to look at then are functions that are not continuous at 0 comma 0. Instead of looking at in general terms for any a and any b, we're just going to be looking at functions that are not continuous right there at the origin, and then see if we can find a limit. Does that make better sense? Okay. So we will look at functions that are not continuous at 0 comma 0. All right. Now, basically there are two types of things we're going to look at here. We're going to look at functions that don't have a limit, and obviously, and functions that do have a limit. All right? So, first of all, I want to look at the case where functions don't have a limit at 0 comma 0. And so let's put it this, case 1. Functions that don't have a limit don't have a limit as x comma y approaches the 0 comma 0. All right. Now, let's see, make sure we understand what that means. We can, here's the xy plane that our functions are defined on somewhere, all right? And of course, here is 0 comma 0. Now, there is basically an infinite number of ways. Okay, we're talking about x comma y, any arbitrary x comma y, getting closer and closer to 0 comma 0. Well, there's all kinds of ways that this point, x comma y, can travel to get to 0 comma 0. It can first, one way is it could go down it could just go down I'm trying to darken this more, it could just go down the y-axis to 0 comma 0. But it also could go along the x-axis to 0 comma 0. There's infinite number of ways. Another way it could travel basically diagonally along the line where the y value equals the x value. Or it could even travel in a parabola, for instance, like this, along the xy such that y is equal to x squared. All kinds of ways. When you looked at functions of one variable, let's just take a detour for a second. Functions of one variable. And you guys talked about continuity and limits of functions of one variable. Okay, they only are defined on, say, an x. So basically, we look at a number line, one-dimensional number line that they're defined on, because it's only one variable. So if we have some number here like 5 on the number line, how many different ways can I approach that number on the number line? 2 ways, right? There's only 2 ways. I can either approach that number from the right, or I can approach it from the left. So you may remember the term or concept of right-sided limit and left-sided limit from Calc 1, all right? Well, the thing is, now that we have a 2-dimensional domain, we don't just have 2 ways you can approach 0 comma 0. We have as I said, all kinds, infinite number of ways. And the deal is, if we get a different limit value as we approach 0 comma 0 along a different path, then the limit doesn't exist at the origin. Okay, and that's very possible. So, let me put this down. If we get different limit values as x comma y approaches 0, 0 on different paths, then what we say is, we say that the limit, LIM, as x, y, arrows to 0, 0 of our function, fxy, does not exist. Does not exist. And the abbreviation for that is going to be DNE for does not exist. Right? So, let me show, there are so many different strange functions here when we're talking about going into 3 dimensions. Let me bring this up. All right. Can I see this? What? Oh, well, it's showing over there. I don't know why it's not showing. There. Okay, you can see it over there. Okay, here's our, let's see, let me rotate this thing around. So this is our function. If you're able to see this thing, look at here, it kind of goes in, and then it's like you're folding, like when I'm trying to wrap Christmas presents, it all gets kind of jagged. You notice it kind of just crinkles a little bit right here, and this is right here at the origin, or this is the z-axis, this vertical blue line. And then if we go look on the other side, we have a similar kind of crimping or whatever of this function. All right, now, as we approach the origin 0, 0 along different paths for this particular function, we're going to get different limits. What I can do here with this is I can drag, this is going to basically give me the limits as I'm approaching it from different angles. Okay, here we're starting with the angle 0, which would be along the x-axis, and it's telling me right up here the limit. So let's see, it's giving me a path. So let's just go forward here. Let's go to pi over 4, and at pi over 4, that means it's basically approaching it like at a 45-degree angle. And notice it says up here that the limit is 1/2. Now, if we go to pi over 2, which is basically approaching it from the y-axis, it's back to 0. We go to 3 pi over 4, it's negative 0.5, and then for pi, it's back, I think it's back to 0 again. 5 pi, then 5 pi over 4, it's back to 1/2. And then in between, it goes through all these other different values for limits. So it's very unusual how this function works. Look at that, as it's going differently. This red line is basically the line of approach, and it's hitting all these different values. It's moving along the surface, but hitting an infinite number of values. So it's a very unusual function in that we basically have an infinite number of limits as we're approaching it from an infinite number of paths. All right? Okay. All right. Well, let's look at a few, a little bit more conventional looking, conventional functions for this. And this is going to be the type of, one of the types of problems that you'll see on your homework or maybe on a quiz or something. And so what we're going to have here is show that the LIM as xy approaches arrow 0, 0 of our function, DNE does not exist for the following function. All right. So what's kind of nice from your perspective is that you already know there's a problem. Okay, so that tells you that you're going to have two different limits depending on which way you approach. But you have to show that you get two different limits. Okay. So our first example here is fxy equal x squared minus y squared over x squared plus y squared. Okay. And we know that this thing is not it's not continuous at 0, 0, all right? All right. So basically, what do we have to do here? What do you think we have to do? We're approaching this 0, 0 along the xy plane. We want to show it's not continuous, which means we get two different limits. So what do we have to try to select? Well, you're in something on the left, something on the right, sort of, but you're on the right track. What do we have to select? That's getting there. What's that now, Tom? Okay, all right. So what you're talking about then is selecting a path, all right? And what we have to find, and that's what you were getting at also, but what we have to find then are two different paths that give us two different limits, all right? So we need to get two different paths that give us two different limits. All right. Okay. And what Tom had mentioned was, why don't we try a path where, say, x is 0 and y is approaching it that way. So let's look at this path number 1. Okay. X is equal to 0 and y is approaching 0. Okay. So that would be, say, like this. Approaching it down like that. X is equal to 0, y is getting smaller and smaller. So what we have to do then is, since x is equal to 0 along this path, we plug in 0 for the x. All right? Because it's going to be equal to 0 anywhere along this particular path. So what we have then is f of 0 comma y, because our x value is 0 along this path, and let's plug in what we have here. So this is going to be, it's x squared minus y squared, so this is going to be 0 squared minus y squared, x squared plus y squared, 0 squared plus y squared. And of course, what this is then is minus y squared on top, positive y squared on the bottom. Now, y is approaching 0. So the limit here, minus y squared over y squared, now we're just looking at when y is approaching 0. So what can I do here with this thing to figure out what this limit is? I don't have to be that complicated at all. No. Yeah, I can just cancel. Notice I've got a y squared on top, I've got a y squared on the bottom. Y is approaching 0. Y doesn't equal 0, it's approaching 0. So this simplifies to the limit as y approaches 0 of just minus 1. Well, that limit is going to be minus 1. So that's our limit along that path. Now let's try another path, and let's try an alternate path where y is equal to 0 and we're approaching it as x gets smaller. So here's path 2, and we're going to go y is equal to 0 and x is approaching 0. Right? So up here, what we have this time around now, we're approaching it along the x-axis. So this is along the x-axis. Okay? All right. So now we have to plug in 0 for y. All right. So what we're looking at here then is f at x comma 0, y is equal to 0 all along this path. And we plug this into our function. Well, this is going to be x squared minus 0 squared over x squared plus 0 squared, which is x squared over x squared. And of course, that's going to simplify to 1. So therefore, our limit, since it's always equal to 1, along that path, the only limit we can have is 1. Okay? So the limit as xy approaches 0, 0 along this path is equal to 1, say on the x-axis. So we found two different paths, though. We found one path where the limit was -1, another path where it was +1. And that's the kind of thing you have to demonstrate, for me, in order to show that there's no limit. So since we get two different limits, two different limits. The limit does not exist. Okay. All right. Now we're going to do two more examples, and in these other examples we're going to be using a little bit different paths. So it's not, you think, oh, I got it made. It's always going to be these two paths. Well, it's not always going to be these two paths. Okay. So let's look at this other example where we have fxy, x comma y, equals x times y over x squared plus y squared. All right, again, this function is not continuous at the origin 0, 0. Not continuous at 0, 0. And again, what we're wanting to do is we're wanting to show that the limit doesn't exist. So let's figure out two paths here. Now, so what can we come up for one path that might work? Okay, we're approaching. We've got to figure out a route here to get to 0, 0. All right. For one of them, yes, we can do the same thing as last time. So we'll use one of those for this first pass. Let's say we'll let x equal 0. All right. And therefore, y will be approaching 0. All right. And so x equals 0, y is approaching 0, so we're going down this way along the y-axis. All right, so let's plug in 0 for x. And what do we get here? Now that's going to be f at 0 comma y. And so now we have x times y, so that's going to be 0 times y over 0 squared plus y squared. I think that's right. Yeah. And what do we get? The numerator is 0 times anything is 0, and the denominator is going to simplify to y squared. All right? And remember, this is, first of all, we're talking about as y gets close to 0. At this point, y isn't equal to 0. Well, what's 0 divided by anything that's non-zero? It's 0. So this is equal to 0, since y itself isn't yet equal to 0. It's traveling down, but it's not 0. So therefore, in this direction, our limit is 0. So the limit is equal to 0 along that path. Everybody okay with that? See how you get that? Now, an alternate is, so if we say, okay, let's go the other way, like this, is that going to work? Is that going to show that we... No, it's not going to work, because we're going to end up getting the exact same limit of 0, and that doesn't prove anything. All right? So we have to pick an alternate path. Okay. In other words, doing this or doing this. Yeah, it won't change anything. Because 0 times anything, positive or negative, is still 0. Okay. Okay, if we're not approaching on the axis, that means we have to say we are approaching on a line going to 0. Well, no, you have to be approaching 0, all right? So it's got to be a path. If you just have 1 for each one of them, that's just a point. That's not approaching 0. That's stuck there. Look at what we have up here in the numerator. We have x and y multiplying each other. There's really, this function doesn't, okay. Think. Yes. If we approach it along y equals x, so what we can do here is now what we're going to do is approach it from this basically like a 45-degree angle. Along that line, x and y are the same, have the same value. Y equals x. That's another valid path to going to 0, 0. Okay. So, path 2, along the path, or along the line, y equaling x. That's a straight line. Okay. So what we can do here then is basically substitute x for y or y for x. It doesn't matter. Yes?
Is it going to be 0 for x?
Huh? No, because now, look at, we're approaching, if you're approaching along this, let me make it a clear diagram here. We're approaching along this line right here to 0, 0. Does x have any 0 values along that line? No, it doesn't. No. So this is y equals x. The only thing we can do here is substitute y for x or x for y in our function and see what we get. Okay? So let me just say, let's replace y with x, because they're interchangeable if they're along that line, in our function. So now we're looking at f basically applied to x comma x, because our y is actually being replaced with the variable x along that line. All right, so what is our function here? X times y. We're replacing y with x, so that's going to be x times x in the numerator. And then we have x squared plus y squared is going to be replaced with x squared. All right? What do we get here? X squared on top. On the bottom, we get 2x squared. Now, this is as x is getting smaller and smaller, going to 0. Now, what can I do? Again, I can cancel out here x squared, and what do I have? Along this path, it's 1/2. 1/2, 1/2, 1/2, getting closer and closer to 0, 0. It's always equal to 1/2. So its limit has to be 1/2. So the limit is equal to 1/2 if we go this path. And that's all we need, is to find 2 of them that are different limits. Thus, the limit as xy approaches 0, 0 of this particular function does not exist, d(n)e). Got to find the second one, second path. Now, I've got one last example where, yet again, we're going to have to use a different path to get to 0, 0. So here's the last one, number 3. Here, fxy is equal to xy squared over x squared plus y to the 4th power. All right. Now again, this thing is not continuous at 0, 0 because we have a 0 denominator. So it's not continuous at 0, 0. All right. We're trying to show the limit doesn't exist, so let's pick an initial path. What do we want to try for an initial path? That'll work. Either x equals 0 or y equals 0, either one of those will work. So path 1, x is equal to 0, y is approaching 0. So again, we're coming down the y-axis. Okay, so we'll replace x with 0 in our function. And so what do we get here? So we have f, x is now just going to be 0. And we have then it's xy squared, so it's going to be 0 times y squared over x squared plus y to the 4th, so that's going to be 0 squared plus y to the 4th. So that simplifies to y squared over y to the 4th. And what do we get here then? This simplifies to what? Oh, yes, thank you. Gosh, yes. I don't know why I did that. Thanks. Yeah, 0 times anything is 0. Right. Okay. And so we have 0 on top, y to the 4th on the bottom. Where are we here? Okay. And let's see. Okay, again, y to the 4th, it's getting close to 0, but it's not. But along that path, it's not exactly equal to 0. So again, 0 divided by anything non-zero is going to be 0. All right. Okay, so the limit along this path, the limit equals 0. Okay. Now, we have to find that crucial path number 2, which will give us a different limit. Let's see. That'll do it. X equals y squared. All right. So just kind of what made you think here, this is our function here. Just generally what made you think of that? Yeah, okay. So Mary's saying is she just kind of saw that if she replaced x with y squared, in the numerator she'd get y to the 4th, but then in the denominator, if you square the x, then, and x is supposed to be replaced by y squared, then when you square that, you get y to the 4th, and we also have a y to the 4th in the denominator. So things will be able to cancel out to a different number. So it's a matter of being able to eyeball something like that, and that's the whole key to it. All right? So basically, we're approaching it this time around. This is actually kind of a sideways parabola, as we remember from our conic sections. So it's going to be something like this. It's going to be approaching like that. All right? Okay, so now let's replace x with y squared, and let's see what we get here. So now our function is going to be, okay, y squared comma y, because we're replacing the x with the y squared. And so we have x times y squared, so that's going to be y squared times y squared over, and then x squared, so that's y squared squared plus y to the 4th. Okay, so this, using rules of exponents, is y to the 4th on top and 2y to the 4th in the denominator. And now we have, very nicely, y to the 4th cancel out, and so we have along this path a limit of 1/2. So therefore on this path, the limit is equal to 1/2. So therefore, the limit of our function doesn't exist. DNE. Okay. I think it's a good time just to take a 5-minute break, and then we'll move on.
You don't want to ask back someone who it was and told them they have the wrong number. They call like 3 times.
Oh, so you've already talked with them that this is the wrong number and they're still calling you back. Are you able to block them or something?
I think so.
I know, I get a lot of different, now you've got people wanting to sell you things that now can call. It used to be cell phones were like an oasis. None of those people knew your cell phone number. Well, that's not the case anymore. So if it doesn't show up on my caller ID, I just don't even do it. If they leave a message, then I'll see what the message is. I won't do that. I'll try to forgive and forget. It must have been. You are who you are. Mary wants to take the first test in algebra as soon as possible because she won't retain it, she says.
Yeah, I know. I try to help her.
Oh, good. She's working ahead a lot. She's almost done with the first unit stuff. I'm a little concerned, though, when she says she doesn't retain it. Yeah, I know. We're already behind. It's interesting. Different classes have their own personality, and that algebra class actually, opposed to most of them, they actually ask quite a few questions. And so that makes a difference. Okay, so we had a series of examples here where we were told that the limit doesn't exist, and we had to demonstrate that it doesn't exist. All right, so here's case, what would I call this? Case 2, then, so to speak. All right, is showing that a limit does exist as xy approaches 0. So how do we show a limit does exist as x comma y approaches 0, 0? Now remember, it has to be the same limit no matter what path we go along. Okay? Now, obviously, if we would spend eternity going through an infinite number of paths. All right, so that's not how we're going to do it to figure out whether the limit exists. We're going to use the squeeze theorem. So I'm going to rewrite that for all of you. It's something that you were introduced to in Calc 1. So, and I'm going to basically give you the two-variable version of the squeeze theorem. If f of xy is less than or equal to g of xy, and that in turn is less than h of xy. So what we have here is we have three functions of two variables where one is bigger, one's in the middle, one's always smaller. All right? And we know what happens with the two on the ends. And the limit of the f of xy function as xy approaches some a comma b is equal to some number L. And the limit of the top one, h of xy, as xy approaches the same a comma b, is also equal to the same number L. Then we know what the middle function does. Then the limit of the middle function, g of xy, as xy approaches a comma b, is also going to be the same limit of L. What we're going to do here in the ones that we're going to look at here is that this L is going to be 0, the number 0. Okay. In what we look at, L will end up being 0. Okay. All right. So before we actually use this squeeze theorem for some functions, I want to show you some inequalities that we're going to utilize. So we will use the following facts. Okay. First of all, x squared over x squared plus y squared is always going to be less than or equal to the number 1. These are all positive numbers, positive, 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 but the denominator is going to be at least as big as the numerator, because we have a plus y squared. So since the denominator is going to be bigger, therefore it's going to be less than or equal to 1. Does everybody agree that that sounds reasonable? And the same way then, if we did y squared over x squared plus y squared, that's also going to be always less than or equal to 1. Again, the denominator is going to be bigger. Now, I can then kind of extend this a little bit and say, okay, if x over x squared plus y squared is less than 1, why not have x squared over x squared plus, say, 2y squared? That's also going to have the denominator is going to be bigger than the numerator, so that's also going to be less than or equal to 1. The only thing that's different here is that we have, say, a 2 in front of the y. Similarly, then, we can say y squared over x squared plus 2y squared is also less than or equal to 1. And you can have all kinds of combinations of this. You could have x squared over 3x squared plus y squared is less than or equal to 1, all kinds of things. And there's one more. The absolute value of x divided by the square root of x squared plus y squared. All right. This is also going to be less than or equal to 1. All right. This is always positive. This is always, the square root, this radical is always defined to be positive. And this is always going to be bigger than x, bigger than the absolute value of x. Remember from algebra, at least I hope we remember, that the square root of x squared is equal to the absolute value of x. Okay, does that ring a bell from algebra? So therefore, this denominator is always going to be bigger than the numerator, so that we have that. And similarly, the absolute value of y over the square root of x squared plus y squared is also going to be less than or equal to 1. So we're going to be using those to use the squeeze theorem. Okay. So let's do a couple of examples here. So use the squeeze theorem, to find the following limits. Okay. For the first example, it's going to be limit as, again, we're just going to restrict ourselves to xy approaching 0, 0 of 3x squared y divided by x squared plus y squared. Okay. Now we want to use the squeeze theorem. Okay. Let's look at the absolute value of, we better do that. The absolute value of 3x squared y divided by x squared plus y squared. Okay. All right. And I'll explain in a second why we're doing that. What's the absolute value of anything always bigger or equal to? 0, exactly. So 0 is less than or equal to this. So this is going to be our low function. Now, we have to get a high function for the squeeze theorem. So we need to find something that this is less than or equal to that's going to help us, all right? Now, look at what we have here. We have 3x squared y in the numerator here. So let's just show another way of writing this. This is really the same as x squared times 3y all over x squared plus y squared. All right? I'm just reordering the multiplication. Now, basically, the absolute value of x squared divided by x squared plus y squared, right from up here, is less than 1. So this is less than or equal to, I'm going to replace this whole thing, x squared over x squared plus y squared, less than 1. And then we have, of course, we have the absolute value of 3y. Now, so this is our top one then, the absolute value of 3y. Okay, does everybody see how I got my low and my top functions here with this, using that inequality? Now, we're talking about the limit as xy approaches 0, 0. Now here, there's no more x in the picture here. But, so what's the limit of the absolute value of 3y as xy approaches 0, 0? X is approaching 0, and y is approaching 0. 0. There is no x in there. It's just going to be the absolute value of 3 times 0, which is 0. Okay. Now, so our top function has a limit of 0. If a function is always equal to 0, its limit is going to be 0. So both the low and high functions have limit equal to 0. Therefore, my middle function has a limit equal to 0 by the squeeze theorem. Therefore, middle function has a limit equal to 0, and that's the squeeze theorem. So therefore, the limit of as xy approaches 0, 0, now my middle function here was the absolute value of 3x squared y over x squared plus y squared. So that equals 0. Okay. Now, if the absolute value of something is equal to 0, as we approach 0, in other words, if this limit of this absolute value equals 0, what can I say about the limit of just what's inside the absolute value? It has to equal 0, right? It can't be anything else. If the absolute value of something, if its limit is 0, if the absolute value of something's limit is 0, then that something has to be 0. You can prove it formally, but I think we can all trust that that makes sense. So therefore, I've shown that the limit of 3x squared y over x squared plus y squared as xy approaches 0, 0 is indeed equal to 0 by the squeeze theorem. Now, the other examples are going to follow the same way, except we may use different inequalities to demonstrate it, okay? So let's look at, keep that up there. Let's see, the limit of 4x to the third y squared over x squared plus y squared as xy approaches 0. And we'll find that. All right. Again, we're going to do the squeeze theorem. So again, we're going to look at the absolute value of 4x to the third y squared over x squared plus y squared. And that's going to be bigger than or equal to 0. So this is, again, is our low function. But with my inequalities, I can make this less than or equal to what? Here's my list of inequalities right up here. Right. Right, absolute value of 4x cubed. Because notice here I've got times y squared over the x squared plus y squared, and that's one of my inequalities here. So that's less than 1. So this thing is less than 4x to the third times 1, which is just the absolute value of 4x to the third. All right, and this then is our top function. Or I called it the high function, I guess. All right, and it's the same deal then. xy is approaching 0, so the limit of this absolute value of 4x to the third, as both x and y are going to 0, well, it just has x in it. I'm just going to, it's a continuous function. I just replace the x with a 0, and I get my limit. So this is equal to 0. Okay, so therefore, they both, the high and low functions, have the same limit. Of 0, have the same limit, equal to 0. So I can say, therefore, that the limit of my 4x to the third y squared all over x squared plus y squared as xy approaches 0, 0 is equal to 0. All right? Okay. And if you can bear it, I'll do one more with just using a different inequality. And that will end this section then. Okay. Find the limit. Again, xy going to 0, 0 of 5x squared times y over the square root of x squared plus y squared. Okay. All right. Again, we're going to look at that absolute value, 5x squared y over the square root of x squared plus y squared, and we know that the low function is 0. Okay, this time around, we're going to use this particular inequality here, the absolute value of y over square root x squared plus y squared is less than or equal to 1. So this whole part right here is less than 1. So therefore, I can put as my high function the absolute value of 5x squared. Well, that's actually just 5x squared. So this is my high function. And again, when we take the limit as xy approaches 0, this thing approaches 0 as xy goes to 0. Okay? So then, by the squeeze theorem, our limit of our function is 0. As approaches 0, 0 over square root of x squared plus y squared is equal to 0. Okay. All right. I hope that seems fairly straightforward. All right, that's what we're going to do with limits and continuity then. And then, oh, guess what? In the next section, we finally get back to something that looks like calculus again. So we're back to that part of it. And what we talk about then, we have time here to get started on this. What we're going to talk about in the next section are partial derivatives. All right? And that's when we are taking the derivative of a function of more than one variable. Now, partial derivatives doesn't mean we go halfway through the problem and quit. All right, so that's not what we're talking about. Now, I'm assuming that most of you have not worked with partial derivatives before, so it takes a little bit of getting used to, takes some practice, and I'll show you why in a couple minutes here. All right, so this is 14.3 partial derivatives. And we'll be using these throughout the rest of this unit, definitely. Okay? All right. For given a function of two variables, f(x), y, it has two separate first derivatives. It doesn't just have one, a single first derivative. It has two first derivatives. All right, we call these partial derivatives. Quote unquote partial derivatives. Okay. Let's just show you some notation first before we, so let's just put notation here. Okay. We have, first of all, the partial derivative with respect to x. Now this partial derivative with respect to x, that's one of the two. And that's denoted either with our function, which usually is the letter f, with an x down there as a subscript. Okay. Or we can use the lowercase delta symbol like this. So frequently, especially if I'm in a hurry here, that's going to look like the number 2 if I'm not careful. But this is lowercase delta. All right. So this is similar to the Leibniz notation with a single variable calculus. Remember that we know that the Leibniz notation is df dx, okay? But this is delta f delta x here, all right? All right, so let me just put versus, and this here is for a function of one variable. All right, and then we also similarly we have the partial derivative with respect to y. Partial derivative with respect to y. And one way of notating it, and I'm going to more frequently use this notation because it's just so easy to use it. So we have again, here we have a y as a subscript, and then the other way is again with that delta notation, d f d, y rather, like this, okay. So two different ways. Now the deal is, okay, well what is the difference between these two partial derivatives, right? This is the crux of, this is actually the central fact, so to speak, of this whole section. So I'm putting a big asterisk there. When we calculate or determine fx, and this is usually how I'm going to say this. I'm going to say fx. I mean, that's just how I'm going to say it. When we calculate fx, we treat y as if it were a constant. And I'll show what we're talking about there in a minute. Similarly, then, when we calculate fy, when we calculate fy, derivative with respect to y, we treat x as if it were a constant. Okay. All right. let me just show you this drawing here, which can help somewhat show what we're talking about here. All right, here we have some surface. This is our function of x and y. So we have the x, y, and z axes, and then here's our surface that is formed by the function, okay? And now, say we're looking at the partial derivative at where x is a and y is equal to b, down there. All right, let's just take this on up to the surface here. So here's the corresponding point up in the surface for that, those values of x and y. All right, now if we basically cut this surface in two ways. One way where we just cut it so that we are going along the y-axis. The other way we cut it is if we're going along the x-axis. So if you can kind of see this, here's the y-axis. The way this surface is, this is as if we're just cutting it with a plane, and what we get is this curve. When we cut into this surface along the y-axis, we get this curve here. They call the curve C2, right? Now, if we cut along the plane in the direction of the x-axis, we cut into the surface another curve, and they're calling that curve C1. And both of those curves go right through our point. Now, along this curve here, where it's going along the y-axis, all the values of x are the same because we're moving along the y-axis, so all the x values are staying the same. Now, when we're looking at the other curve there, this curve is going along the x-axis. The y values are staying the same. Okay. So we have these two curves going through this point. One of the curves, the x values stay the same. The other curve, the y values stay the same. And then what we do is basically we calculate the slope of the tangent line there. So basically we look at the derivative in each direction along, say we just pretend now we're all strictly along this curve here, and we calculate the derivative along that curve. That gives us remember that the slope of the tangent line is the value of the derivative. Remember this from Calc 1. Okay? So therefore, but here, when we calculate the derivative, we're keeping the, along the y-axis, the x values are staying the same. Okay, so up here, this is our, this here then is the tangent line that has that slope of the derivative. So here, for T2, basically, wait a minute here. Right. The x values stay the same. because we're going along the y-axis, and this derivative then gives us the fy. Along here, for t1, this is the tangent line here along this curve. The derivative that we get there is fx. Here is where the y values stay the same. Okay. So we end up with one derivative where it gives us the slope of the one tangent line along the y-axis, the other derivative that gives us the slope of the tangent line along the x-axis. Right. I might have something that I can bring in on Friday, which is a more dynamic thing than just a single little page like this. All right. Let's actually look into just calculating some partial derivatives here. Before we get into calculating or determining, I want you to recall two facts from functions of one variable. What's the derivative of a constant that's not connected or multiplying a variable? In other words, just by itself? Zero. Okay. So the derivative of, and I'm just going to call it a constant all by itself, is equal to 0. Okay. We're going to use that fact. And then what if we have a constant, say the number 5, and it is multiplying a variable? What do we do with this constant? Yeah. We take the 5 here and we multiply it by the derivative of the 2x, so that gives us 10x. All right. So therefore, if the constant is, the fact that I want to say is this: if the constant is multiplying a variable, we keep it. All right. This 5 is essentially there, except it's multiplied by the 2. So I'm going to put this in quotes, we keep the constant if it is multiplying a variable. And these two basic facts from Calc 1 is going to be what you use to guide you through correctly getting these partial derivatives. So let's look at some examples here. Let's look at fxy, function of two variables, and it's a polynomial thing, x to the third plus x squared times y to the third minus 2y squared. All right. And what we want to find are the two different partial derivatives. So we want to find fx, and we want to find fy. Now, for fx, let's start with that. I think it can be helpful at first to actually write this on your paper. For fx, we're going to treat y like a constant. And this may help you to stay focused to remember that. So and we go term by term. And we're going to keep in mind those two rules that I just put up there. So the first term, I hope, is easy. X to the third, its derivative with respect to x is 3x squared, right? All right, now let's look at the second term. Remember, we're treating y like a constant here. Y is essentially multiplying my variable. It's on the back end, but it's still multiplying my variable. And it's considered as if it were a constant number, not changing. So therefore, what would this derivative be of that second term? But I'm still taking the derivative of x squared. 2y to the third, well, wait a minute, we reduce the exponent of the x by 1, so we're still going to have an x there, right? X squared is going to go to 2x.
2x, y to the
Yes,
third.
yes, yes. 2x, y to the third. The y to the third is going to basically remain unscathed, so to speak, but it's got to still be there. Now the 2x squared, we're going to get its derivative and get 2x. And then finally here, what am I going to get then for minus 2y squared?
Yeah.
0, right, because that's treated as if it were a constant number. We don't have any variables here, so that's just going to be 0. So this right here is our fx with respect to x. Now let's go and do the fy. Now with fy, it's reversed, and now, and I'm going to write it down here, we treat x like a constant. Okay. All right. So here, this is where we're starting. This is what we're working with. So x is a constant. So that first term becomes what?
0.
It just disappears to 0. So let's go to the second term. Now we're doing the derivative with respect to y, but we have an x squared multiplying. Somebody else besides Jenna. 3x squared y. Yes, that's right. Never mind. You're right. Where am I here? Yeah, right. Because we're doing the derivative with respect to y, so we're going to get a 3y squared. But that x squared, x is a constant, has to stick around unscathed as it is. And then finally, we have our last term, minus 2y squared, minus 4y, just plain old derivative of that. Notice then that what we get here, these are two separate things. They don't look like each other necessarily at all. All right? So they're two separate derivatives. Okay. Okay, the geometric thing here, and I'm going to bring something on Friday that works better, is that it gives you we have, for along any surface, let me see how good my drawing is going to be here today. So we have some surface, all right, that's from our function, all right, and we're looking at a particular point. And let's say that here's our x direction, and here is our y direction. And of course, our z direction is up here. All right. We want to basically cut the curve, the surface, in two ways. We cut it along the x-axis, and that gives us a curve. When we cut it with a plane, that gives us a curve. So here, along this curve, this is along the x-axis, y has the same value. Y is equal to a constant there. The slope of this, so this is a curve. It has a tangent line. The slope of this tangent line, is equal to the value of the derivative going along the x direction, equals fx. All right? Then we can also cut it along the y direction, and here x remains a constant. We have another tangent line, and the slope of that tangent line is the fy, because we're going in the y direction. Remember, if a slope is positive, is something going increasing or decreasing? It's increasing, right? So and the slope is negative, it tells us something is decreasing. So slopes, if the slope in one direction is positive, that means the function along that direction is going up. But if the slope in the other direction is negative, the function is going down in that direction. So basically, these give us a lot of information about how the function is going up and going down in the two different directions of x and y. Okay, so therefore, the slope of, so let me just put the slope of this tangent is equal to fy. So it's, and hopefully with that other thing, it'll also become clearer. I think we have time we're just going to cram everything we can into this class. So let's just do one more example here today of a partial derivative. And I want to let you all keep in mind that the chain rule is certainly alive and well with functions of two variables, all right? So let's look at this function of x and y equal to the sine of x over 1 plus y, right? And we want to find, first of all, let's find fx. All right. So with fx, we want to make a notation that y is treated like a constant, or treat y like a constant. Okay, chain rule. Derivative of the sine, that's going to be the cosine. And we put whatever we have unscathed right there in the parentheses. We don't change that. And then, of course, times, then we have to take what is inside of this. And so let me use this other notation. So what's inside is x over 1 plus y. And we have to do its partial derivative with respect to x. All right? Chain rule. So let's figure out what this is here. Okay. I know. It's a delta, not a 2. My 2's will have the thing continue on down. All right. Okay, so I think you said what it was.
You end up getting 1 plus y over 1 plus y quantity squared.
Well, wait a minute. Now, y is a constant, so this is like a number.
Just 1 over 1 plus y?
Yeah.
Derivative of the top times the bottom minus derivative of the bottom, which is 0.
Yeah. Okay. All right. So you're wanting to do which will work. You're wanting to do the full-fledged quotient rule with this. All right. And that'll work, but there's a simpler way to look at this. Let's look at this x over 1 plus y. It can be looked at as 1 over 1 plus y times x. All right, yes, easier way. Your way will work. You just got to be careful, all right, but it'll work. So here, we're treating y like a constant. So this whole thing right here, one's a constant, we're treating y like a constant. That's just a big constant laying around. And we do our derivative of x, which gives us 1, all right? So basically, this becomes then, so let's put this first, 1 over 1 plus y times then the cosine of x over 1 plus y, like that, all right? I think we have time to figure out the fy. The fy, we're going to treat x like a constant. Okay, so first of all, we do the derivative of the sine, which is the cosine, x over 1 plus y. And then we're going to be doing the derivative with respect to y of the inside, x over 1 plus y. All right, now x is the constant, y is the quote-unquote variable. Now here I'm going to go on and just use the quotient rule with this. although you could fiddle around with it and not have to use the quotient rule. But I'm going to do that. So let's use the quotient rule. All right, so what do we get here? All right, so we have our denominator 1 plus y, so we square that, right? So we have 1 plus y in parentheses squared. And then we take the bottom one, 1 plus y, and we multiply it by the derivative of the top. Yeah, the derivative of the top, x is just a number, a constant, so the derivative of the top thing is just a 0. Then we have a minus, and then we take the top function x and multiply it by the derivative of the bottom, which is just a 1. 1 plus y, derivative is 1, all right? So this, if we simplify this, this becomes minus x over 1 plus y squared, like that. And so then we can just finish this. Our partial is minus x over 1 plus y parentheses squared, and then times our cosine of x over 1 plus y, all right? Okay, so we'll continue with this, doing some more examples, and we'll see how far we get on Friday.